Great. Now we're live with this webinar on the methodology behind HUGSI.green. I would like to welcome all live visitors here today, but also you guys that watch this after on demand. And we have a pretty good lineup here, both on the guest attendee side, but also on the speaker side. You can already see me, Erik Svan. We have Rohan Kaur with us. You will be able to present yourselves a bit very soon. We're also waiting for Andrew Collum to join us. Coming in here is Andrew, perfect, from Overstory. So we will have a nice time together in the coming 60 minutes together. And we hope to make this a very interactive session together. So please use the chat section on your right-hand side. You can ask questions there, and you can give different emojis and send to us if you want some hearts appearing. So let's make this interactive. And this is actually a remake, you could say, of one of the favorite webinars we made already 2020, 4 years ago, on the methodology behind HUGSI. And I think that's the methodology is one of the areas where we get a lot of questions. So definitely that's something we want to be very clear and open with and to share with you guys. So that's what we're going to do today. And if you want, from the attendees, please say hello in the chat. Tell us where you're based, because I know we have guests from many different continents and countries, and also in the call today from the presenters. I'm based in Sweden. Andrew, you're in Italy right now, or?
Mm-hmm. Yeah,
and,
it's me.
Rohan is based in India. So I think we have a pretty advanced setup here today. And I guess most of you have seen me before, Erik Svan, so I won't go into deep depth on me. So perhaps, Andrew, you can start by just saying hello and telling us a bit about who you are.
Yeah, hi everybody. I'm Andrew Cottam. I'm working for Overstory as a geospatial quality lead, and my background is in remote sensing and conservation. And at Overstory, we analyze large amounts of satellite imagery and do analysis of specifically of vegetation. So looking at the health of the vegetation, the height of the trees, and the extent and land cover mapping as well. Mainly for the utility sector in America, for looking at threats and risks to power lines, but and some other areas as well, like in HUGSI, for example.
So remote sensing and vegetation, that's sort of your niche in a way, but for different use cases. Cool. And then over to you, Rohan, or data scientist in India.
Yep, thanks, Erik. So, hello everyone. I'm Rohan. I'm working as a data scientist in Husqvarna, and I closely work with Erik on HUGSI and been part of the HUGSI journey for last 3 years now. And my background is in software engineering and data science. As part of the AI lab here in Husqvarna, we work on different projects where we try to use AI and make services and make services better through AI, and that's basically my role here. And HUGSI has been a special project because we have made a lot of incremental growth in HUGSI, and looking forward to this.
Fantastic. And we hope this to be a pretty nerdy session where we go into depth into things. And I think also in the lineup of guests, we have pretty knowledgeable people in the area, in remote sensing and in analytics. So I think that there will be a good discussion. And on the agenda side, we will keep introducing a bit. We're going to go through all the different steps necessary into producing the data that we have. And of course, that's important to understand how to interpret things and make use of it. Then you also need to understand how it's produced. And to produce anything like this, you need to make a lot of definitions. What is what to measure, where to measure it, when to measure it. Those things we will go into. For many people, just analyzing green space from space is magic, or can't really understand it can be done. And I think that's really cool. And hopefully we can demystify that a bit. So Andrew will go through together with us on how to analyze the green space and all the work you do on that side. And then we're going to hand over to Rowan, making sense of the data. That's the part that we're doing at Husqvarna, making sense of the data and structuring it in a way that we can share on the website. And finally, I will also share then how this data is being used in the platform. And we will end up with a Q&A. So please add questions in the chat continuously, and then we'll wrap up and take it up in the end and wrap things up. So that's sort of the lineup for this meeting here today. Great. So I think let's get started. And HUGSI, the Husqvarna Urban Green Space Index, it's a service from Husqvarna providing objective and recurring monitoring of hundreds of cities. It's 279 at this point in more than 60 countries, 61 as of now. And what we hope to bring here is a new baseline on urban green space data that is made available to municipalities and cities all over the world. And we've shown that we have a scalable model, so we can onboard any city anywhere. And we provide recurring annual updates of the data. And I think that's quite unique. And we use global open data sets to produce this. And that allows us to do this in a scalable way. So those are things that we want to share in the sessions, so you all understand what that brings. Part of what we do is also that it's objective monitoring, and we will explain how the monitoring is actually done. And being objective is, of course, important, so it's not politicized or anything like that. It's comparable between the cities. We're using the same sensors, the same data set, and we calculate the KPIs using the same methodology for all cities, making it comparable between cities, comparable over time in a relevant way. And we hope with this be open with our methods to share that it's a trusted and scientific methodology behind this. So data can be relied upon. And I think that's really, really important. So that's what this session will be all about, how we make this objective monitoring, the recurring analysis, using the global data sets with this trusted and scientific methodology. And first things first, if you're going to measure something, you need to understand what to measure, where to measure it, and when to measure it. Then we can discuss how we're doing it. But what, where, and when are very important questions, and something that we started back in the days in 2019 when HUGSI was first sort of conceived, developed, and launched during that year. What are relevant numbers to look at and produce here, and where to measure and when. And to begin with, we also were looking for input data set that makes sense here, that should be globally available, that we can rely upon. We are not producing the raw data, but trusted organizations do. And we will come back to that later, but the main source of information, of course, is from the Sentinel-2 satellites, part of the Copernicus program in the European Space Agency, and that provides the global reach there. We're using the OpenStreetMap administrative boundaries to understand where the cities are located. Where does a city start and end? Where are the administrative boundaries? So that's also a very scalable and easy way to use open source pointers on where the boundaries of a city is. So that's another key component. And to understand the urban parts of cities, where are people actually living? Because that's what we want to focus our efforts on. We use the human settlement layer, also produced by the European Commission, but on a global scale. And we recently upgraded this as well to the most recent population data available. So I think that's a good improvement also that we brought up on our latest launch event. So these are important things to state, that these are the main data sets that we're using. And the green KPIs is the what part here. And here we try to establish relevant measures for overseeing the urban green space on a city level. Of course, it can be further broken down into smaller pieces and areas in the city, but in general, these are important things to monitor as a snapshot, but also over time, looking at historic change and trends coming up. And here we usually go into like, how are these defined? And you will also learn from the coming segments today more about how they are produced, but presented of urban green space, that's quite self-explanatory in a way, but a very basic KPI for a city to monitor. How much of the total area of our urban parts of the city, the built-up areas, are covered with vegetation. Could be lawns, small forests, trees, green roofs, shrubs, whatever vegetation is in there. Whoever owns the land, everything is brought in to this analysis, covering the entire urban parts. That's the first and main KPI here. Then we need to understand a bit more about what we are measuring here, and dividing vegetation into two classes, tree and grass is what we do. We'll mention more about how we do that, but I think one of the more sought after or popular KPIs among the municipalities is, of course, the tree canopy cover percentage. How much of our city is covered with tree canopy? And that's also something that we provide for the entire city with yearly updates like that. And the percentage is, of course, the share and proportion of tree canopy within the city compared to the gray area, impervious area, built up hard-made surfaces, the blue areas covered with water. So I think these are the main four land classifications that we use. Andrew will come back to that later. Those are like just looking at the vegetation in a way, how it's the proportions of it. Then a normal thing to look at is also the proportion of green compared to the number of people living there, the per capita numbers. There are some recommendations from the World Health Organization on how much green space should be available, but I think they are quite low, set on 9 square meters. Most cities have far beyond that, but a few struggle still on that level. But as we can see, the higher population density in the city, the lower amounts of green space is available, of course, and comes down to the competition of land use. But still, many cities are looking at the urban green per capita KPI, and that's very relevant to track, but hard to really sort of manage as a growing population increase the competition and stress on the land use. Distribution of urban green space, we made a special on that in the 2022 event, explaining that in detail, and I won't do that now, but it's available on our YouTube channel. But essentially looking at the distribution, how well spread is the green space in the city? Is it condensed and centered in one big park, or are there trees on every street and small pocket parks here and there? And from a human perspective, of course, a high distribution is far better than a low distribution. It's all about access and the availability of the green. You need to have it close by to really benefit from it. Looking at the vitality and health, that's also, of course, relevant in a city, on a city level, to find areas of high stress or changing vitality. So those are important parts there, and we'll come back to that as well. And producing these KPIs every year gives the unique ability to also plot them and look back at the history over time. So those are very important aspects for us. So that's a bit of the what. The where and when are also very important, defining the urban areas. And this is more of a storyline where we either get boundary shared by the municipality, or we use OpenStreetMap to set the outer boundary. And of course, for a municipality, it's important that we are not sort of mixing up data between municipalities. So you account for someone else's data or someone else's mistakes or something like that. So that's the first step. Next step is to filter out the urban areas here. And I think in general there we're looking for populated parts that are deemed to be urban. And in general, we're looking for areas of at least 1,000 inhabitants per square mile, or converted into these 100-meter grids of human settlement layer, means 3.8 people per 100-meter grid. So it's not super dense, but it's also lots of areas in the city that is not accounted for here. In this illustration, you also see an island up here, a small suburb here, and we bring in all islands of at least 5,000 people, inhabitants, given that they are also deemed to be urban. But if it's smaller than that, it's not included. And this is pretty strict definition. Not all agree, but this is how we have set it up to make it work on most cities in a good way. We want to increase the comparability in the city over time, given this. We want to improve also the ability to compare between cities, because the build-up and the layout of cities are very, very different. Is it a city located close to the sea, ocean? Is it something that is a city completely surrounded by forest or farmland, or is it desert around? It's hard to compare if you are not able to filter out those factors. It's also the urban areas that are really hard to keep green like that. That's where you have the competition. So if your natural state, like in most areas, is green, like in desert areas, the normal state is sand and not green. When green is the default, then it's easier to be green in lower population areas. So that's why we're filtering this out. And that's a very important thing to bear in mind, because comparing tree canopy cover assessments can differ greatly depending on, of course, which areas you are bringing in. And sometimes we're punishing cities where you have when you're surrounded with forests, because we're looking at the urban parts. And to somewhat compensate for that, we're adding a 300-meter buffer. And of course, the 300-meter, what does that come from? Well, it's a definition we made that means that we take in 300 meters of the ocean outside of the city, for instance, or 300 meters into the forest or into the grassland surrounded. And that also resonates with other definitions of what's available. Not all people wander into the forest for kilometers or miles, at least not without the backpack and some snacks. It's not bad to have it, but to really make the KPIs work, we have this kind of strict definition. And I know, Andrew, if you can help me shortly on this one, but the when question is also very important. That many other like data is collected during the season where you don't have leaves on the trees. And that gives some advantage if you want to look at individual stems, for instance, but it's mainly also used for other kind of infrastructure data collection in the city. So it's not made entirely with the green space use case in the first place. But for HUGSI, we are actively trying to find the best day, the greenest day available. And that's what we want to bring in when we're assessing the city. So that's super important. And please step in.
I'll come on. I'll come on to that. Actually, in my slide, there's a slide on finding the greenest day. So yeah, continue.
Yep. Cool. So I think that's at least a statement covering then what we measure, where we're measuring, and when we're measuring it. And if you understand these constraints, and you don't have to always agree on the method, but you know it, and then you can value the data from that. And I think we have stick to this method now for the latest 5 years, and it has proven pretty valuable given this comparability that we're after between cities, but also for a given city. So we hope to stay on with this. And please add any questions related to this in the chat, and we can pick it up in the Q&A in the end. So that's a sort of a first glance at this and the what, where, and when. So let's step into the details a bit more now, analyzing green space from space, how it's actually done, Andrew. And please guide me here. Let's flip slides.
Yeah, okay. So first of all, thanks, Eric. And I'm just going to take you through the details of the methodology that we use within HUGSI. And this is all based on a sensor called Sentinel. I'm assuming fairly base level knowledge. I'm sure that there are plenty of people who have got, hang on, let's just move to the right. I'm sure there are plenty of people who have got good knowledge of remote sensing, but I'll start from the basics. But it's a European Space Agency satellite funded by the European Commission. And it's one of the great things about the data is it's public, open and free to every country in the world, even countries that have left the EU, like Great Britain, etc. And the Sentinel series of satellites, because there are two satellites, it's a constellation, Sentinel 2A and 2B. So there are two satellites that are spinning around the world at the same time, covering different parts. But they capture reflected radiation from the Earth's surface in a number of different bands, and across 13 bands in the case of Sentinel-2. And that information is extremely valuable for determining land cover class and a whole range of other environmental applications across the world. It has global coverage. It doesn't quite cover the poles because it's slightly off the poles, but it revisits on average about every 5 days, depending on where you are in the world. So it's really quite an amazing.
Not so much green space on the poles yet either.
Yeah, it won't be long though before we start seeing the land under the pole, North Pole. Yeah. And the spatial resolution, depending again on the band, is 10 meter or 20 or 60. And so it was launched back in 2015, and so we have data going back 8 years, pretty much globally. Next slide, please. And so this is a very complicated looking slide, but basically what this is showing is this is showing Oh, let's get nerdy.
Yeah.
So across the bottom is the wavelength of light that different sensors are detecting, and at the top in the red box is Sentinel, and you can see a number of different grey squares. I don't know why I'm pointing at the screen; nobody can see. But there's a number of grey squares, and they are basically capturing light at those spectral kind of resolution, that spectral amount. So for example, at the bottom we can see Landsat, and now the two lines at the bottom are showing this is an American sensor, and they've got a blue box and a green box and a red box, and that's visible light. And for Sentinel, there is an additional band 1, which takes into account cirrus cloud, and so it's really good at taking out cirrus cloud from the imagery, which we'll come on to in a bit. But basically, it has very similar spectral band properties to Landsat, and Landsat's been flying for nearly 40 years now, but it's at lower resolution at 30 meters. The only thing that Sentinel is missing is the thermal bands, these ones on the right-hand side. So it's difficult to pick up heat energy from the Earth. And in fact, that would be quite useful for cities, because obviously the more surface ceiling you get in cities, the more concrete you put down, the more heat there is, and the hotter cities get. And that's one of the reasons why it's good for cities to go green. Next slide, please, Eric. So the first thing that we do is we download the Sentinel imagery, the Sentinel-2 imagery, the raw data, and there's basically this is what's called top of atmosphere. So when the satellite is flying at 800 kilometers and imaging the Earth, it's seeing everything in those 800 kilometers, including smoke and cloud and cirrus cloud and everything in between. And that makes it quite difficult to actually do the remote sensing on and the land cover classification, because you've got so much interference. And so the first thing that we do is we process this top of atmosphere data to what's called top of canopy, or surface reflectance. And what that's trying to do is it's trying to model what the light reflectance is going to be when you're right down, close to the ground. And so ESA provide a number of algorithms for doing that. And they have a set of calibration sites. So as the satellites go over the world, they fly over these calibration sites, which are basically kind of, I'm not sure if they're called dark bodies, but they calibrate sensors, and that allows them to remove a lot of the atmospheric interference. Not clouds, unfortunately. It would be great if satellites could just wipe away clouds, but they can't. So we actually have to identify clouds, and then that's effectively no data, because for surface reflectance and for visible data, you can't see through clouds. You can with radar, which is a different satellite. This is a Sentinel satellite that has a radar sensor on it, which can look through clouds. Okay, next one. Oh, one thing I missed here is identify the greenest pixels. So in the pre-processing step, we try and find basically the time of the year when the city is the most green, because obviously if you're trying to compare between cities, it's a bit unfair if you just say, in the northern hemisphere, let's pick the summertime, let's go in June, because obviously in the southern hemisphere, that's the least green. So we have to look across the whole year and try and find those times of the year when the city is the greenest. And in order to measure the greenest cities, we turn to something called the next slide, Eric.
Yeah.
Next slide. Oh, no, it's not. It's too late. But I'll come on to that in a second. Yeah, this one here.
Yeah.
Actually, it's the one after that one. So I'll come on to that. Just go back to the classes. I'll talk about those. So we take the raw Sentinel imagery. We get the surface reflectance, and then we remove the clouds in the pre-processing. And then we do the land classification, where in this case, we're trying to identify 4 specific land cover classes. So obviously water, urban, grass, and trees are the 4 classes that we use for HUGSI. Next one. And in order to find vegetation, one of the bands within Sentinel-2 is incredibly useful because it picks up, this is what's called the near infrared band, and there is incredibly high reflectance from chlorophyll because within the layer of the leaf, in this spongy mesophyll layer, that it dramatically reflects near infrared. So when you're looking down at the earth and you get high reflectance in the near infrared, it makes that band seem very, very bright, and that basically gives you a really good indication of healthy vegetation. And the more the reflectance, the more chlorophyll and the more vegetation you have in that case.
And I think this is an area where people are a bit surprised what you can do and so on, and that it doesn't really, we're looking for the green parts, but doesn't help painting stuff green, doesn't make them green to us. It needs to be vegetation. So it doesn't have to be even very green if you're looking at the very dry out and brownish lawn. It's still vegetation to us. And a green roof is still vegetation, and a plastic football field is not vegetation, it's plastic. So even if it, for the eye, might look like it's green space, it's not.
Yeah, exactly. So in those cases of like the roof and the plastic grass, you wouldn't see that. You'd have a really dark reflectance in the near infrared. Next one.
Yep.
And so one of the things that you can use to measure the amount of vegetation effectively is this thing called a normalized difference vegetation index. And it's a ratio between this near infrared and a red band. And it can measure very accurately how much vegetation there is. And also it can be a measure of how healthy your vegetation is as well. So you can look at the same areas through time, and you can see the NDVI change fairly dramatically over the season. And so what we try and do is we try and profile that change in NDVI over the year to pick basically the peak, and then we use the satellite imagery from that peak period to get the land cover.
And that's how we find actually the right day to analyze for the city.
Yeah. But it's actually quite complicated because generally speaking, the time of the year when the vegetation is healthiest is when it's raining the most, because and so there's going to be more cloud around, and so it's very hard to get cloud-free imagery during the growing season, especially in the tropics. And in some cases, you may, even though there's a revisit every 4 or 5 days, you may have to wait a month, possibly even 2 months, to bring together enough images of the city to give you complete coverage. Because don't forget that when Sentinel is flying around, it's not doing I suppose it's doing a few hundred kilometers across each time. So each swath, when it flies over, it's doing about 260 kilometers. And but that doesn't mean that your city is entirely within that one band. It might be on the edge or whatever. So sometimes you have to wait for different revisits, and that can be quite complicated. Is putting a mosaic together of all these images to cover your city, especially cities like Sao Paulo, which are enormous. Actually, do we do Sao Paulo? I'm not sure.
Yeah, we do Sao Paulo. Absolutely.
Okay,
I think that the clouds is an enemy of us, looking for the nitty-gritty details there. And Andrew, we actually had a question also from Johan here, covering especially this topic. How do we separate trees and grass, or even shrubs, he mentioned in the question. So please, stepping into this.
Okay. Yeah, that's actually answered by this slide in many ways. Yep. So when you're looking at a satellite image, then one of the things that you can use is the spectral information. But increasingly, and the way that HUGSI has been developed is we're using machine learning models, or what are called deep learning models, which uses a slightly different approach. So they're not just using the spectral information from the ground, from the imagery, but they're using what are called features within the imagery that differentiate between, let's say, grasses and trees, and these things are called convolutional neural networks. And they had this reputation of being black boxes, and in many ways they can be seen like that. But basically, you give the model lots and lots of locations where you know what the land cover is. So you feed in many thousands of examples of water and urban, grass and tree into the model, and then you what's called train that model, and it learns to differentiate between those different land cover classes. And so it could be based on things like, for example, if you have a forest, it might be that the variability between the pixels is more because you've got shadows and you've got some areas that are, you know, shaded and some areas that are bright. So maybe the variability between the pixels is more than grass, for example. Or it could be something else. It could be something that, you know, we're not immediately aware of, but the convolutional neural network will pick up these features and it will use them to discriminate between these different classes. And then at the end of that, you have for every pixel, so for every 10 by 10 meter pixel, you'll have these probabilities, and that's a probability between basically 0 and 100 of one of these 4 land cover classes. I hope that answers the question.
Yeah. And I think the shrubs is either trees or grass, like that. But how would that be modeled?
Again, when you're, I mean, semantically, shrubs and trees are quite difficult to differentiate between because, well, I mean, basically there's no agreement on when is a tree a shrub. There's some definitions that say a tree has a single branch, a single trunk coming up, and shrubs have multiple trunks coming up. But, you know, it's very difficult to have a hard and fast rule about when is a tree a shrub and when is a shrub a tree. But generally speaking, when we do the training, it's fairly apparent when you've got large areas of grass and large areas of trees, and the model is pretty good at differentiating between them.
Great.
Next one. Change detection. So how am I doing for time, Eric? A few more minutes.
Well,
okay.
we can speed up a bit. It's always nice.
Change detection. So obviously, because we're using Sentinel, we have, in theory, up to 8 years of data. But what we're doing right now is we're doing change between the previous year and the current year, and we take into account the prior knowledge. And what that means is we look at the distribution of the land cover classes in the previous year, and then we compare it to what it is now, and we use some rules that say, for example, if it was water, or if it was urban in the previous year and it's water now, that's pretty unlikely. You know, that's not a common land cover change from urban to water. So we have some kind of weights on these changes between the classes for pixels, and then we get the overall changes for the pixels, and then those are summarized for the hexagons that you see in HUGSI. And so it's basically the majority class within each hexagon. So if we have 75% of the pixels are grass, then the hexagon is classified as grass. Next one.
Yeah. Cool. And
yeah, so
and things like that. It's also a common question.
Yeah. The resolution we use, so the native resolution of Sentinel is 10 meters by 10 meters in the visible bands, and we summarize that up to 1 hectare hexagons. And but in most cases, higher resolution does not necessarily mean better, because if you're looking across, let's say you're taking a Sentinel 10-meter resolution image, you're, by its very nature, averaging your land cover class within that 10 meter by 10 meter pixel. And so when you're looking for fairly broad habitat types like urban or grass or woodland, actually 10 meters is probably enough. You might get some pixels which have got mixed habitat within them, but having a higher resolution, obviously you then pick up different features that don't map to those nice tidy 4 classes. So you might find cars, or you might find roofs from buildings, or you might find level crossings, or things which look really spectrally different. So you then have to think about your classification. Am I doing the right classification, or should I change my 4 classes to something that's more representative of that high resolution imagery. So it
So
doesn't
the
necessarily
resolution
lots of,
type, Andrew, so the resolution type we have now, kind of coarse, but it helps us actually to focus on these 4 land classes that we have of
yeah,
water, urban, trees, or grass.
exactly. And I think, you know, there is a drive. People do want to have the highest resolution possible, but it's not always necessary. And, you know, for many years, people have done analysis on you know, take, for example, climate and weather. There's a 1 kilometer square resolution imagery called MODIS, which basically shows you clouds and gives you a rough idea of where pressure systems are. And it's perfect for predicting the weather. Although not very good at weather predicting, but you know, but that kind of satellite is 1 kilometer by 1 kilometer, and that's been going for many years. So yeah, higher resolution is not necessarily better. Next one.
Yes, and this is also a common question, like quality, accuracy, and assurance.
Yeah. When we train a model, we split all of the training data into well, effectively we have all of the samples which we've done. We split it 80% into training data, 10% into what's called validation data, and 10% into test data. And those things help you identify the accuracy of your model. And this box on the right hand side at the bottom shows you some statistics about how accurate. So basically, this square is called a confusion matrix, and on the left-hand side is the actual class if you were on the ground, and on the top would be the predicted class. And so these squares basically show you how good you are at saying, is this tree actually a tree? And so the figures at the bottom where it says R91 and R78, 36 or whatever, the average accuracy across the whole model is about 75%, which is about average pretty much for land classification exercises.
Yeah.
Next one.
So that's reasonably good, you could say.
Yes. Oh, that's me finished. There you
go. And let's. I think then we have gone through the details and the nitty-gritties into how we analyze the green space from space, and I think that's a core part. But very important is also how we make sense of the data. So I want to invite you, Ron, up on stage here to tell the story about how we are doing this, because now we're doing it as we normally do it. Andrew and Overstory are responsible for producing the material that we then put into our own pre-processing and data ingestion. So Ron, please tell the story.
Yep, thanks Eric, and thank you, Andrew. So this is how it happens. Once we get the data from Overstory, the idea is to have a smooth data ingestion and pre-processing so that we can further make sense of the data. And I think we have a very good, data pipeline set up in HUGSI where we load and save the data to our AWS cloud services. And then what we do is we kind of pull the data from there, and we try to make some basic checks, especially if there is data that is missing. Let's say we received a city that was there in 2022, but it didn't come or it didn't show up in 2023. So we do some basic checks like that. We also make sure that whatever key values that we get out of every city, they are consistent for all the cities. It shouldn't be like one particular city has a tree canopy cover, but other city doesn't have it. So we kind of make sure that those basic checks are done. And then one crucial part is restructuring the GeoJSON data. So the maps that we see on the HUGSI for each and every city, you have different versions of the maps. I think one crucial part is to restructure that raw data that we get from Overstory. I think there is a lot of data there on a hexagon level, and we kind of make sure that we utilize the most relevant ones. So restructuring those data becomes very crucial, because at the end of the day, when we kind of put everything on the site, there is a big pressure created because the data is very heavy. So we need to kind of optimize that part as well to make sure that the data is optimized. It is easily loaded on the site, and it doesn't be like data is unable to load. So we kind of mitigate. We have to mitigate those issues or challenges there. So it becomes crucial to restructure them and then kind of generate the Mapbox tiles out of those data. And then once we are done with more or less the restructuring and then some checks and balances, we kind of try to generate the different KPIs and insights from the data. We try to make more sense of it. And I think Eric, you can move to the next slide.
Yeah, and before that, perhaps I just reminded that we spend a significant amount of time in the servers calculating data, and especially with the new biodiversity data. I think you share how many days was that for processing?
Yeah, I think the biodiversity part was, I think, very. This was a very new and challenging thing, and
Yeah.
I think I took it like 15 or 16 days to process the entire data because I think at the back end we have set up a very sophisticated algorithm that identifies and spots the biodiverse areas. So I think one of the reason being 15 and 16 days to process that data was that some of the cities are really big in size. So if you see some cities which are in China, they have a file size of around half a GB file. So it's like 500, 600 MB files. So kind of running an algorithm on a 500 or 600 MB file becomes really tough. So yeah, I think even though we are running it on a cloud service where we have a good compute level, it kind of takes a lot of time. So yeah, I think that's a very good point, Eric.
That's pretty advanced.
Yeah, I think for the time we are here, it's pretty advanced. I do see that as a challenge, and hopefully we'll try to optimize that even more. But I think biodiversity was a very different and it's a very niche thing that we have added to HUGSI. So yeah, have to agree on that. Yep, I think we can move to the next. Yeah. City grouping. So yeah, one of the important things that we realized when we had this HUGSI data is that it makes sense to kind of group the cities into different categories. The reason being that many cities are kind of correlated to each other on certain aspects. So, for example, you could see that cities which are in Europe, they would have similar conditions. So and then if there are cities which are in Africa, they would have similar conditions or similar kind of vegetation or similar kind of tree canopy coverage. So it made a lot of sense to kind of group them together, and that's what we did. One of the groupings that we have done is basically the regions, which is basically you put it into different continents. So if a city belongs to Europe, then you put everything, all the cities in Europe, group them together. If a city is in Africa, you put all the cities in Africa and group them together. So regions is one of the groupings that we do. Another important grouping that we focus on is the climate zones. So I think we have categorized it into 4 climate zones: the north zone, north temperate zone, the torrid zone, and the south temperate zone. We don't have any cities in the polar zones yet, but yeah, I think grouping the cities into different climate zones becomes crucial because climate kind of plays a very vital role in adjusting or in defining how the vegetation will look like. So most of the cities in Europe seem to have an upper edge when it comes to kind of greenness, and that's because they belong to the north temperate zone. And if you see the south temperate zone, there are a lot of African and Latin American cities which have a different set of climatic conditions, and that kind of defines their vegetation growth or the tree or grass growth. So it makes a lot of sense to kind of group them on climate zone. Then the next grouping that we did was the population density crisis. I think it also becomes very important to group cities where based on this population density, because for a very long time we have noticed that cities which there is a high correlation that cities which have higher population tend to have less green space. And cities which have low population, there's a high chance that they will have a, they'll have a more green space. So it made sense to kind of categorize the cities on population density. So I think we have categorized them like 500. If 500 people per square kilometer, it's a different category. If it's 500 to 1500, then it's a different category. So we have categorized that, and I think it gives a good insight as well to that.
Exactly,
Can
and
you?
this is about the comparability
Yeah.
topic, finding relevant cities to compare with.
Yes, exactly. And I think we have ranked them as well in based on these different groupings. So based on a different grouping. So if it's
Yeah.
the North Temperate Zone, then which cities are ranked well on the North Temperate Zone, or which cities are ranked well in Europe? So I think we have the ranking as well
Yeah, and
on that.
speaking about ranking, that was sort of the starting point of the
Yeah.
index, sort of.
Yeah, I agree, Eric. And I think this is a very special one. I think the index gives us a more probabilistic estimation of the city's greenness. We have a formula derived that we kind of use to give calculate the index, which is a more normalized approach to kind of bring all the cities on the same table and then kind of view them together and see how we can calculate the probability, which gives us the idea like what are the chances that this city has a greenness level of so and so. So it kind of gives a good estimation, and once we get that index, which is basically a value between 0 and 1, because probability is kind of value between 0 and 1. Once you have that, we kind of rank them on that. So higher the index, you are ranked higher, and lower the index, you are ranked lower. And yeah, this is I think this is kind of the crux of the ranking that we define here in HUGSI.
Excellent.
And again, to score well or to have a higher index value, a city should have very well distributed, high coverage percentage of trees and grasses, also good health within the populated parts of the city. So we focus on the grass cover, tree cover. We also focus on the health of the grasses and trees, but we also focus on the distribution of the grasses and trees across the city. And all this is kind of taken together and then put into a probabilistic approach to calculate the index and then eventually come to the ranking. And also, since most of the municipalities prefer to have look at the trees more, the trees are kind of have a higher weight as compared to grasses. So in our formula, we have rewarded the trees twice as much as the grasses.
And on that point, I think the global community totally agrees that trees are the most valuable green asset out there. But we've been really searching for evidence on what weightage we should put into it. And we haven't really gotten any good input from academia yet on what should be a good multiple there. So right now we're sticking with the twice, double value of trees compared to other vegetation.
Yep, absolutely.
Hmm.
Yep.
Let's look into rating and green score, because we started with the index and the ranking, but we wanted to have something that is a bit more wider and where we can have specific criteria in a way. So tell us a bit more about how the rating and green score is calculated.
So green score is more of a cumulative score, which we calculate for each city based on the different KPIs that we have. So it's not any probabilistic estimation. It's more of a high level, sum up the different KPIs and see which city scores well. And then it kind of gives you an indication of how much green or how much greenness you're going towards. So green score is more towards that. And then the rating that we calculate is based on this green score that we have calculated. So if you have a higher green score, then we have kind of categorized you as a A plus. But if you are on the bottom side, then we have given you an E minus. So I think green score kind of gives you a very good picture on a high level of how green you are based on the different KPIs. So I think this one focuses more on just the KPIs, but yeah, I think it's on a high level. It's a very good estimation, and I think rating is also a good indicator of how well the city is doing in terms of the green score. So yeah,
Great.
next.
And I
Eric,
think
just on conscious of, I was just going to say, conscious of time. That's great. You're on to questions now. There's a few questions in the chat.
exactly. So let's skip into the questions now. And I think we have covered the most important parts here, and we have also answered some questions in between here from Johan. I hope you're happy with the answer on trees versus grass and bush. And we had a question here from Ralph Mintz as well on the selection of 300-meter buffer, and if it's in a way related to the 330-300 rule of Dr. Kononendijk. And now it was conceived before the 330-300 rule, but already back then there were some sort of understanding about 300 meters is of course not the precise number that is important, but in the behavior of people that within a circle of 300 meters, I'm very free to move and likely to move, and where you can actually bring the value from the green space within 300 meters. Doesn't mean that 500 meters is impossible, but that was sort of the way of thinking there. And then other have also adopted 300 meters as a good measurement there. But 330-300 is a very important KPI actually, or a method, a rule of thumb that many cities are actually adopting going forward. And I think there's also a similar question from Roloff there with the response from municipalities and how like effects of HUGSI. And here there is a very big difference, I would say, between municipalities in different parts of the world, how data-driven they are, how much they have started to adopt different type of KPIs when it comes to green. We are very sort of narrow and focused on only green, and of course green space is important, but it's not the only factor that builds a thriving community and a sustainable community, but it's one important thing. So especially like happenings like the 330-300 rule and the adoption of it has put attention on KPIs and data in this, and especially like the 30 part, the 30% target of having a certain amount of canopy cover, 30% canopy cover in your community. That's something that we can deliver on directly. The 300-meter rule is sort of in there because we have the distribution numbers and the buffer that you mentioned before. The 3 there is hard, but I think the adoption of KPIs is growing in importance, and I think that canopy cover is one of our main things. The change data that we produce every year as well, like what's the negative or positive net of changes in the city. That I think will be a coming KPI of importance, especially linked to new legislation where you as a city or a country, especially in Europe now, you are not allowed from 2032 to reduce green space. And as you still have to have sort of some sort of development in your city, you need to find ways to balance pros and cons or plus and minus in adding and removing green. So that will be a key thing that will have great impact, I'm sure. Let's see what we have more. What impacts have you noticed recorded from this data collection practice? From Chloe there. Well, we have seen the adoption of reporting on green space is growing on the cities using HUGSI and cities in general. So there is an ask for green space data in a new way. It's one example that we usually bring up is where they are spending a lot of money on greening a city. Then they want to have objective and recurring measurements going like that. It's not the driver for it, but it's something that can help explain the development, that you're sort of reaching the targets. That's really hard to tell in another way. Of course, you can measure the number of trees you're planting, but we can measure the effect. And I hope that we can tell a stronger story on the impact that brings at a later point. But we started to see evidence where they are actually applying HUGSI as like the smartwatch for urban greening that we want to be. Marie, you're asking if there's a way to estimate the age of a tree or group of trees in a given GPS location. Well,
I can. I was going to say I can do a bit of that, and then I'm going to have to jump in just a sec. But yeah, sure. I mean, obviously, there are lots of things that affect tree size and age. Environmental parameters and soil, and a whole range of different things. So there's lots of variables, but there are some relationships between the canopy size, which obviously you can see from space, and the age of a tree. And you can, in some cases, single species specific, you can approximately age the tree and also based on the height, but it's very, very young science, and generally speaking, not very easy to do. And the other thing you can do, obviously, is look at overall biomass for forests and for trees, and there is a specific sensor now called JEDI, which is doing just that.
Exactly. Thank you, Andrew. And if you need to drop out, please do that. Thanks a lot for joining. And we're just wrapping up as well. Right. And I want to thank you all for participating. Also, Rowan, of course, for joining us and helping us telling the story. Let's see if there's any other questions coming in as well. Then we can try to answer them as well. If you want to stay on, we can do that. But thanks for staying on for this full hour session. It's pretty packed. I think we could have continued for another hour as well, but it doesn't really end here. You're more than welcome to reach out to us in any of our channels, review our website, check out our LinkedIn page. Please follow us so you're up to date on what's happening. There's lots of content also on our YouTube channel. And what we didn't cover so much in depth today was the new biodiversity data of HUGSI, where we have a full hour special also on that, stepping into the nitty-gritties and details and definitions made there. So that's also extremely relevant, I think, for you. So watch that. And thanks all for joining. And please connect with us. Reach out to our email, hello@HUGSI.green, if you have any additional questions. And if you're watching this after this live event, please type questions in the comment box below, and we will for sure answer that as well. So it starts here. The journey starts here. Hopefully you learned more about how HUGSI is produced, and you can benefit from the data even more. Thanks a lot. See you around. Goodbye.
Thank you. Thanks, Eric. Thank you, everyone. Bye-bye.
Bye-bye.